Hello, and welcome to NHP's webinar on fault withstand ratings for switchgear assemblies. My name is Shane Townsend, Power Distribution Technology Specialist for NHP Electrical Engineering. This is just one in a series of webinars created to showcase NHP's smart devices powered by smart distribution and embedding smart safety into operational processes, providing our customers with better visibility into processes, data, and analytics. So why are we interested in learning about fault ratings for assemblies? Communicating a fault rating is a critical design parameter to a switchboard builder, system designer, and ultimately the end user. The ratings we ask for and offer have to make sense for the type of components within the board. There is a common trend to ask for a bigger fault rating than what would be necessary. This can lead to something that you intended to be a panel board or a load center ending up looking more like a main switchboard. ICW for 1 second is normally requested, but why? 15 kA DBs and 80 kA main switchboards, where do these ratings come from? At the end of the day, having a sound understanding of what fault levels are available and most appropriate will lead to the most economical solution. So what we will cover in today's webinar are the requirements for assemblies in relation to AS3000 and AS61439. We'll look at the types of fault rating in 61439, some single line diagram examples and how these might be interpreted. What we hope you walk away with after the presentation is an understanding of the different fault withstand ratings available, being ICW, ICC, and ICP. Understand how the specified fault withstand rating is likely to impact the assembly's construction and its practicality. So now we will have a look at some of the definitions which broadly define a fault and have a look at the requirements of our assemblies under these conditions. A short circuit is a fault causing current significantly in excess of the continuous rating of the circuit. The fault could occur downstream, external to the assembly, on a circuit that our assembly is supplying, or the fault could occur inside the assembly. The risk of an internal fault is usually reduced with an appropriate form rating. If this fault current exceeds the withstand rating of the board in magnitude or time, it will have adverse effects on the board. When rating a board for fault withstand, we are mainly concerned about the maximum faults that can occur. This is the three-phase bolted short circuit fault. The below is taken with reference to the technical report 61439 part 0. Short circuits within correctly designed systems are a very rare occurrence, but when they occur, they place abnormal demands on our assemblies. It lists some of the stresses: extremely high forces between conductors, very high temperature rise in very short times, air ionization, overpressure due to arc breaking. It goes on to tell us that assemblies should be capable of withstanding these thermal and dynamic stresses resulting from the short circuit. So what are the requirements of the assemblies? The first critical piece of information required is the end user or someone acting on their behalf must specify the maximum fault level that may occur where an assembly is to be installed. When specifying this, we're talking about the prospective fault current. So the end user must define the prospective fault current, which is derived from the strength of the supply source to deliver current under a short circuit condition of negligible impedance across all three phases. The level of the current is dependent on the supply strength and any latent impedance in the system up to the point of the assembly. The prospective fault level is in our electrical system is expressed in thousands of amps, usually represented by the symbol Ka. The prospective fault level at any point in the system can vary with the level of resistance or impedance in the circuit from the source or the calculated point. We always go for the worst case scenario, which is the three-phase fault. This needs to be defined before we can start designing our switchboard. Now that we have our specified maximum faults that can occur, we can move on to selecting appropriate equipment for our assemblies that is capable of withstanding the nominated fault, just in case the worst case ever occurs. AS 61439 Part 1, Clause 9.31 states that assemblies shall be capable of withstanding the thermal and dynamic stresses resulting from short circuit currents not exceeding the rated values. So what is meant by withstanding the thermal and dynamic stresses? When subject to a fault not higher than the rated withstand, the assembly must remain safe. This means the insulation is not damaged. Creepage and clearance distances remain above limits. Isolating devices maintain their isolation rating. After the fault, there are to be no exposed live conductors. The IP rating must be maintained. Protection circuit, so the earth, must remain intact, and during the fault, we have to make sure that things do not explode and physically injure a person. It does say that some parts may require service, but the main idea is that our assembly remains safe. It is important to note that these requirements are for short circuits and do not cover arc faults. NHP have an upcoming webinar on this topic. So let's take for an example a bus bar chassis, although the same theory applies to any equipment that we select for our assembly. For this test, we will pass the rated prospective short circuit current through the chassis for a nominated time to arrive at a withstand rating. As the video plays, we can see the bottom terminals of the chassis are shorted together using copper busbar of negligible impedance. This ensures the short circuit is seen by the main busbar of the chassis. What we just witnessed is the chassis sustaining a certain fault level for a given amount of time. We can see that there was no significant damage to the chassis and it would be fine to use again. This would be an appropriate selection up to the ICP of the fault level that the chassis was tested to. From the previous tests that we just witnessed, we arrive at two crucial figures. The first value is the I squared T, or the current squared multiplied by time. This is known as the energy integral. This value tells us the effect of heating, which can cause thermal failure, parts to fuse, insulation melting, and thermal expansion, and can cause significant physical damage. By extrapolating the current and time values of our available fault, we arrive at our energy integral. For example, if we have a specified 6 kA fault for 1 second, the energy integral would be 3.6 times 10 to the 7. We can also do this for the equipment in our assembly to see what level it can handle the energy without damage. Mathematically, we need to ensure that the energy integral of all the equipment we select for our assembly exceeds the energy integral available from the fault at that point of the installation. The upcoming video will show what happens if the energy integral of our chassis is exceeded. You can see from that video why it's very important to make sure we get this selection process correct. The time, or the T, of our calculation is best reduced by employing protection devices upstream of our equipment that operate in milliseconds rather than seconds. The second value we arrive at is the peak current, or I peak. The peak current of the prospective fault represents the highest instantaneous value that could occur during the fault as opposed to the RMS fault. The peak current causes significant magnetic forces which can break supports, bend bus bars, and throw around cables. From testing, we can assign our equipment a peak rating which we should not exceed. The following video shows what happens if the peak current rating of the chassis is exceeded during a short circuit fault. Again, the peak current available can significantly be reduced by implementing multi-case circuit breakers or fuses, which will operate under a short circuit condition to reduce the peak. The last requirement of our assembly is to consider if we have appropriate upstream protection devices. AS 3000 2018 clause 2.5.1 states that active conductors must be protected by one or more device that automatically disconnects the supply in the event of an overcurrent or short circuit before the overcurrent attains a magnitude or duration that could cause damage because of excessive temperatures or electromechanical stress in the electrical installation. This means we can and should take into account the upstream protection device when considering our fault withstand rating. The way we do this is we can compare what the energy let through of our circuit breaker is to the equipment in our board. So just like when we do our K²S calculation for our cable selection, we can do the same thing with our I²T of our assembly. This means even if our ICW rating is lower than the prospective fault current, we still can conceivably use the assembly provided careful selection of the upstream device. For example, an S400NJ breaker seeing a 415 volt fault with a 20 kA prospective fault current. The integral energy that would be let through the breaker is approximately 3.1 times 10 to the 6, as can be shown on the table on your screen. If we compare this to the fault available without the breaker acting at 20 kA for, let's say, 0.1 of a second, the energy integral would be 4 times 10 to the 7. This is more than 10 times greater. When we do this calculation, we should also consider our I peak in a similar fashion. The graph on the left-hand side of the screen shows similar information, but for the peak withstand rather than the energy let through. As we've shown a few videos of what it looks like when we get it wrong, I just wanted to show again a video of how it looks when we get it right. Now that we understand the requirements, we will have a look at the type of rating that is stipulated in AS 61439. (61439) Part 1, Section 9.3.2 tells us the information concerning short circuit withstand strength and how we should communicate this information. Depending on whether or not there is a short circuit protection device and the location of the protection device, this will influence the rating that we give our assembly. It is very important to understand what the different fault ratings mean, as they will place restrictions on what protection device can be installed upstream or as the incoming device in our assembly. AS 61439 states that for assemblies with the short circuit protection device incorporated in the incoming unit, the assembly manufacturer shall indicate the maximum allowable value of the prospective short circuit current at the input terminals of the assembly. This is the ICP rating. It is the default in the standard. It gives the assembly manufacturer the most freedom as they can nominate the best incoming device to achieve the ratings required. For assemblies where the short circuit protective device is not incorporated in the incoming unit, or the protective device is in the upstream assembly as is commonly the case, the assembly manufacturer can indicate the short circuit withstand strength in one of the following ways. The first option here is a rated short time withstand current, or an ICW, along with the rated peak withstand current, IPEAK. ICW is usually the most flexible for the system designer, as they can use the ICW and IPEAK ratings to do their own calculations and nominate appropriate upstream protection. The other rating they can choose when the protection device is upstream to the assembly is the conditional withstand rating. This is the best of both. A specific upstream protection device is nominated, which the assembly manufacturer refers to. This will typically give the most economical solution. We will have a closer look at these three ratings before we look at some practical examples. The ICP rating is when the incoming device is protective and is an unconditional rating. I'll draw a box around everything inside our assembly for clarity. The incoming device could be a circuit breaker or fuses. The fault withstand rating of the assembly is the maximum prospective fault current that can be connected to the board. An example would be 20 kA RMS. There is no time associated with this rating as the incoming device protects the assembly for the energy integral and the peak currents. We can use cascading from the incoming circuit breaker for the sub-circuit and sub-main breakers. The ICW rating is for when our incoming device is not protective. Again, for clarity, I'll draw a box around everything that's inside our assembly. The fault withstand rating of the assembly is stated as fault current for a period of time. For example, 10 kA for 0.1 seconds. Using this rating, the installer or system designer can determine what device to use upstream and whether or not the board is able to withstand the fault level at the point of the installation where it will be installed. This is typical for a board with a low break switch as the incoming device. We cannot use cascade from upstream breakers as it is not stated, although we can use cascade between breakers internal to the board. After that, the breaker can be relied on to protect the conductors and downstream parts like circuit breakers or contactors. The ICC rating is the conditional rating, and we can have any incoming device for this one. Again, I'll draw a box around everything inside our enclosure for clarity. For this one, we can see that our protective device is located outside of our assembly. The fault withstand rating of the assembly is stated as a prospective fault current conditional on a certain breaker being upstream. For example, 20 kA RMS with S250 NJ circuit breaker upstream. Using this rating, the installer or system designer knows to use a specific device upstream to ensure the board is able to withstand the fault level at the point of the installation. The upstream circuit breaker protects the assembly, hence there is no specified time applicable for the fault current. We can use cascading of the stated upstream circuit breaker for our internal devices. The main point here is that we must know or stipulate the upstream device when using this rating. So when we're working out the fault withstand rating of a board, we're always looking at the weakest component in the system. It is best to use conditional ratings both with the upstream breaker and also within the board, especially where high fault levels are required. We will typically refer to the cascade tables to improve the ratings of 6 kA or 10 kA miniature circuit breakers. We need to be very careful with the selection of our incoming device with respect to the rating we are trying to achieve. And it always makes sense to aim for the lowest rating possible that will serve the purpose. Some things we need to watch out for: direct connect meters in high level switchboards, as they normally have a very low withstand. Contactors also, standalone, have a very low withstand. They need a protective device either upstream or in the assembly to protect them. The cable on the load side of the incoming device also needs to be considered. We can see some rough calculations here of how the fault level will increase the requirement of the incoming cable. A 6 kA for 0.1 second fault would require 16 mil squared as a minimum. If we were to increase the time on this fault from 6 kA for 0.1 second to 6 kA for 1 second, it would increase the cable size to 50 mil squared. If we plan on using non-automatic devices as incomers, we need to be aware that they have a very low withstand and there are strict conditions on which they can be installed in higher fault level environments. Now we'll have a quick look at some example single line diagrams and how requesting different withstand ratings will impact their design. We'll start with the example where the KA rating is quite low. The prospective fault level at the point of installation is stated to be 5.2 kA. This is straightforward and is easy to achieve. There is no point using a conditional rating here. A typical offer would be an ICW of 6 kA for 0.1 seconds to enable us to use miniature circuit breakers without considering the upstream protection. The next example includes a low withstand device, and we'll see if you can spot it. The prospective fault level at the point of the installation is 8.6 kA. This may seem quite simple, and at first glance, it is tempting to use an ICW rating of, let's say, 10 kA for 0.1 second. What you may have missed is the load shed contactor. Without upstream protection, contactors have a very low withstand, definitely lower than 10 kA for 0.1 second. So, if ICW rating is not appropriate, let's have a look at what our options are. We could apply a conditional withstand rating. This would require us to stipulate a specific upstream device that could lend protection to our contactor. If this is not possible, the next option would be to use the ICP rating. This would require we replace the load break style contactor with a protection device. The last option is we can use the ICW rating. However, this would require that a separate protection device for the contactor be installed in our system downstream of our incoming load break switch. In this example, we will look at how our three options could impact the selection of our incoming device. The prospective fault current nominated here is 14.7 kA. As is typical, this has been translated to a 15 kA for 1 second rating being requested by the end user. If we wish to satisfy the 15 kA for 1 second, we would need to upgrade the incoming isolator to 800 amps. We could consider downgrading the time rating to 15 kA for 0.1 seconds. This is quite reasonable, as most modern protection will clear the prospective fault in less than 1/3 of this time, in which doing so, a normal 400 amp low break switch will achieve the rating of 15 kA for 0.1 seconds. Alternatively, we could consider using a conditional rating, an ICC of 15 kA with no associated time. Again, this requires us to nominate a specific upstream device that will lend protection to the 400 amp main switch and other equipment within our assembly. So looking back on what we have discussed, we have learnt about the requirements of our switchgear assemblies. We have looked at the different withstand ratings available for switchgear assemblies and how they are derived. And we have also looked at some practical examples and how the different ratings can impact the final assembly. Thank you for joining us for this webinar. I hope you have found it beneficial, and if you'd like to watch it again or to find more webinars in this series, please go to nhp.com.au or our dedicated NHP YouTube channel. If you have further questions about fault withstand ratings for switchgear assemblies, please contact your local NHP sales representative. With smarter and faster decision making and seamless connectivity spurring new collaboration, NHP is enabling the connected enterprise.